Good afternoon, evening, or morning, depending on when you're watching. So this is physics, day number 12, and we're going to be looking at, rather than Newton's laws of gravitational and gravitational fields, we're going to look at Einstein's view. Okay, last day I went like for a massive amount of time, like 45 minutes. This one will be shorter than that, hopefully. I'll try not to be so long-winded. Okay, so what we want to look at today is we just want to look at Einstein's theory of gravity. And we're going to be looking at three effects of it, or three or four effects of how it works. So we're going to explain his theory a little bit, how it relates to general relativity, how it bends light, black holes, things like that. So let's set up our plan for this period. Okay, I'll try to keep this one short today. So this is day number 12. Fields unit. We're looking at Einstein's, spelled wrong. It's ENI. Okay, so under Einstein's theory of gravity, we're going to be looking at the theory. Okay. And along that, we're going to be looking at some ways to describe the theory. Some of the metaphors, some of the ways it's described. Okay. We're also going to be looking at effects of gravity in space. And that's kind of what we're going to look at. I'm going to keep it shorter than I should have really split it into two more evenly packed ones than what I actually did last time. So anyways, the first thing we're going to talk about is Einstein's theory of gravity. Okay, now Newton said that any two objects had an attraction based on their masses and their distance apart. And this kind of puzzled Einstein when he thought about it, because he said, how can objects millions and millions and millions of miles apart or thousands of kilometers apart have fields and forces between them? And so he thought about it, and then he came up with the description that anything that has mass actually curves the space around it. Okay, so that's how he described it, is that gravity isn't really a force, it's more of an effect. Okay, it's an effect based on massive objects out in space. So that effect is that anything that has mass curves space around it. Okay, in fact, some objects are so massive that they curve space so much that light can't even escape from them. That's black holes and things like that. So let's basically do the basic background of what we need to know about Einstein's theory of gravity. So Einstein says, oops, wrong side here. Sorry, guys. There we go. Okay, we're not going to get into it mathematically. That's beyond us. Okay, so what he said was that the gravity is not a force, but an effect. Okay, of massive objects. or any object with mass. Okay. Okay. He said that any object with mass curves the space around it. Okay. This curved space causes the effect called gravity. Okay. So the more massive objects are, the more they curve space. Okay. And the problem with this is that it doesn't uh, it doesn't really explain this theory, and this is only the very basics of it. It doesn't really explain um, that well. It's an incomplete theory. He never really got everything explained. Like, where does mass come from? Okay, and then that's where they start talking about things like matter and antimatter, things like that, and all that kind of stuff. But they did. This is his effect. So um, we can think of it in a couple ways. So we think of a few metaphors. Think of the curvature effect along using following metaphors. So think of space as a flat sheet with a massive object on it. Create gullies or holes of gravity. Curved space. Okay, so if we drew that out, it kind of looks like this. Okay, so if you're thinking about it, if we have a flat sheet, okay, let's do a massive ball. Let's do it in blue. It's kind of sitting on a sheet. Then if you have it on a curved sheet, let's do that in black here. Okay, and it's sitting in there. You kind of get, let me draw it here. Don't draw it until I get it kind of figured out a little bit, because I'm not the best drawer in the world. So it would bend the sheet. So sitting in the sheet, and you would have like okay, and then this. Let's do this one over here. Okay, there's your sheet, and this ball sitting on it, and it kind of brings it down. And there is a curvature gully around this sheet that's curved in here. Okay? And the more massive the object in space, the more that we see the curvature. So this would be if this is a massive object, it would be deeper down into the sheet. Okay, this is your flat sheet. Put it on top, it sinks down into the sheet. Okay, and that's kind of how it works with that. So, and these attract any object. So, if you put a great big basketball on the sheet, and then it would have a dent, and then you roll the ping pong ball. The ping pong ball, as it's rolling along, would get sucked into the divot of the basketball and start going around it. Okay, until it eventually decayed into it. If it wasn't going fast enough. Sorry, guys. Excuse me. So that's kind of the metaphor of curved space there. Okay, not the best drawing in the world, but let's just kind of pop up. I'm just going to pause here and bring over a little bit of a YouTube video that has a little bit better of a diagram than this. So let me do that. Give me a second to do that to show you what I'm talking about here. Okay, so I got a video here that talks about some of the stuff that we're going to be doing in our last unit, special relativity. I just kind of got it started here. This will give us an idea of gravitational theory, and we'll talk about it more when we get into modern physics. So this talks about special relativity. Let's just watch this dude here.
Which he developed in 1905. This and other publications of that year put him on the map as a force to be reckoned with. A decade later, in 1916, he published his general theory of relativity, which described the geometry of space itself and revolutionized the way we think of the gravitational force. An adequate description of general relativity requires extremely complicated math that goes far beyond the scope of these tutorials, so we won't even try to touch it from that approach. But we can still briefly describe some of the conceptual implications of the theory that will dramatically change your perception of the universe. So let's see what Einstein had to say. For centuries, we thought that the universe obeyed Euclidean geometry. This is the kind from high school geometry class, where parallel lines never intersect, the angles of a triangle add up to 180 degrees, and all kinds of other geometrical perfections hold true. With general relativity, Einstein showed that this is not the case. Just the way you can distort the shapes drawn on a piece of paper by bending the paper, space itself is distorted or bent around massive objects. That is to say, that just the way that bending a piece of paper results in a two-dimensional plane becoming wrapped around a third spatial dimension, the three spatial dimensions of space are wrapped around a fourth spatial dimension, according to the distribution of matter in the universe, as mass is the property that causes space to bend in this way. This is physically impossible to visualize, so don't worry when you find that you can't do it.
That's true.
Our brains can only comprehend three spatial dimensions, and so the best we can do is to employ analogies like the bending of the piece of paper, and understand that space does the same thing, which is illustrated in an image like this, where a two-dimensional representation of space-time is curved around a star or planet. This does not accurately depict the true curvature of space. It is simply the best we can do. These conclusions describe the universe as non-Euclidean. Parallel lines can indeed cross if they move through curved spacetime. Einstein derived this theory in an attempt to expand special relativity, which applies only to inertial reference frames, to include all reference frames.
Don't worry about this stuff too
called
much.
General relativity. One result of this is the idea that the source of an acceleration has no effect on the force imparted, such that a ship in deep space accelerating at 9.8 meters per second squared would impart a force.
Okay, so that stuff we do later when we get to modern physics. So that gives you an idea of how Einstein revolutionized gravity. He thought of it as curved space. Okay, And there's a couple other effects that we're going to talk about here. That guy there gave you some better diagrams of curved space. And if you want, you can research on YouTube there, and there's quite a bit on general relativity and special relativity. And we will be doing that when we get into modern physics, which is our last unit. We'll be talking about it. We won't be doing the math because the math is beyond our scope here in high school. When I took special relativity in university, even it's fairly complex, and general relativity is really complex. So let's talk about this curved space thing with a couple other analogies or effects as well. So there's the flat trampoline. They call this the trampoline effect. If you visualize the Earth as a massive object sitting on a trampoline, the trampoline bends, then you have that curvature in it, and then that's what attracts other objects towards this massive object. The effect is called gravity. Now, this is where, as he said in the video, you get people talking about that fourth dimension, right? The fourth dimension we can't visualize, but it's just that dimension that causes the space to curve, okay? And they say that parallel lines can then intersect. Well, let's look at an analogy that explains that. So if you were sitting on the Earth and you were a couple of, let's get an Earth here. Let's make a circle. Okay, so we have a spherical Earth. Let's put the center down first. Okay. And here's our equator. Can't draw straight here. Okay, Earth. And if you were sitting here and here, if this was ship A and this was ship B, okay, and they were traveling towards the South Pole, okay, they would actually, here they would be, I don't know, let's say 1,000 kilometers apart. And then to them, they would appear that they are going in a straight path. Okay, that they would look over, well, if they could, and they would go in a straight path. And here's the South Pole, but they would actually follow a curved path to the South Pole. So it's supposed to be curved, not a triangle. Let me try this. Try to get the curve draw. I'm not the best draw person, especially on this tablet. Okay, so you kind of have a nice curved path. So you kind of got a parabola. Okay. So these two individuals sitting on a curved surface like this, on a curved surface, okay, they would only be down here when they get close to the South Pole. They only might be 1 kilometer apart. But yet it appears to them, to the ships, captains, it appears they are traveling in a straight line. Okay? Where in actuality, if we zoom out lots and lots, but they actually follow a curve. Okay, the curve of the Earth, and they don't even notice that. Whereas It's the same kind of idea as if you were dropping things towards the earth. If you were way high up and you drop two objects, it would seem like they're falling straight down, but they're actually falling towards each other slightly, because eventually they're going to hit right at the center of the earth. Okay, appears that they're going in a straight path or falling straight down, but they're actually following a curved path. Okay, just like these ships, and that's an analogy on curved space. Now, it's impossible to visualize this in 3 dimensions because we only think in 3 dimensions. But when you have to think about mass causes this fourth dimensional curve in outer space. And you can think of it like the trampoline analogy, or an analogy of two ships on the earth traveling to the South Pole, following a curve in their path. And another thing that massive objects do is that they will bend light as well. So for our last little thing here, I don't want to go much more than half an hour today, because yesterday I went way too long. How curved space explains bending of light. So now most people say, well, light travels in straight lines. Like the guy was talking about with the Euclidean geometry, we think straight line, everything's straight nicely. Yeah, well, it appears to travel in straight lines, but then as it gets close to a massive object, like the sun, it will bend. And an analogy to that is something like this. Let's say we draw here, get our tool out, and draw where's my shapes here? Oh, gotta go to tools, that's why. All right, so let's draw the sun, or let's draw the earth here. The sun here. Let's say here. Let's make it a sun here. Okay, and then we've got a star over here. Okay, and this is where, well, we have to put two positions of the star. Excuse me. Let me do that properly here. So what happens is the light coming from a star, let's put its actual position. Its actual position will be here somewhere. Okay, and this light is coming from it. And as we get closer to the massive object, there's a big gully, and it starts to bend. This is maybe too much bend. And then we see it there on the earth. Okay, so this is the path of light. Okay, it follows the curve. This is the sun. This is a path of light. Okay, this is an exaggerated bend. It's probably a lot less than that. Okay, kind of. I should be going way, way, way on the other side of my page and then have a slight curve, right? And what we actually see is, because our eyes are used to seeing straight paths, this is the apparent location of the star. Because we see this is virtual light. Okay, that's what I'll spell it right there. Okay, where virtual light is something that our brain thinks it's going in a straight line, so it must be over there. Same thing happens if you look through a piece of glass or something. It vertically displaces a little bit, and it's just shifted over a little bit. Okay, and then this is the Earth here, and what we see, the light comes to the Earth. We think that it's over here, but it's actually over here, and it's displaced some distance because of the bent path of light. Now that's a really big exaggeration on the bend there. Okay, this should be like maybe 7 times farther back here and then have a slighter curve. But that's another effect of the Einstein's theory, okay, of gravity. So that's the difference between Newton. Newton said it was a force, and Einstein said it was basically an effect, okay, of massive objects. It's gravity, the bending, that fourth dimensional bend in space time. Okay, so let's watch one more YouTube video here, and then we will call it a day. So let me just pause it and get that one queued up for us. Okay, so we're going to finish up our video this guy here explaining how the general relativity of gravity is better than Newton's law and how it works. We only went partway through, so we'll finish this one up and see what he says.
We now understand that space is warped around massive objects. We see that general relativity is a big improvement on Newton's law of universal gravitation in terms of a satisfactory theory of gravity. Newton outlined aspects of the gravitational force, but he didn't know exactly what gravity is or how it propagates. Now we can regard it as the warping of space that deflects the path of other objects, like a bowling ball pressing down on a membrane. This curvature creates what we know of as gravity, being that massive objects tend to fall towards more massive objects. And this explains the orbits of the planets around the sun, as well as the falling of objects towards Earth, without having to resort to a magical field force imparting action at a distance. Space is therefore no longer an empty expanse, just the way that time is not a detached parameter. These two constructs are actually part of the same thing. They comprise the space-time fabric. Space-time tells matter how to move, and matter tells space-time how to curve. General relativity, just like special relativity, enjoys a tremendous amount of corroboration by experiment. One necessary result of the theory is that light should follow curved paths around massive objects.
So this is a drawing that I was
trying. And a famous experiment observed light from a distant star curving around the sun during a solar eclipse, whereby the blocking of the sun's light allowed us to directly observe the light from the star behind, which appeared in a shifted location. When light is deflected around more compact objects, like black holes, the light from the more distant object can bend around the mass in a way that results in multiple images of the object. This phenomenon is called gravitational lensing, and it is a common astronomical observation. General relativity predicts and explains all kinds of other observable phenomena, like anomalies in the orbit of the planet Mercury and things like neutron stars and black holes, which we will cover in the astronomy course.
We kind of look at that a little bit
strong as the theory of general relativity is, it is not complete because it has not merged with the particle world. That is to say, we do not yet know how general relativity can be reconciled with quantum physics.
To understand that later a little bit.
We need to do a comprehensive survey of all particles so that we know exactly what we are dealing with. So let's move forward now.
Okay, that's about as far as we're going to go. So that's a little bit about Einstein's theory of relativity and his explanation of gravity. Okay, this guy's pretty good online. He's pretty simple in the way he explains things. There's lots of decent ones on there. And when we get into modern physics, we're going to look at that a little bit more. So I'm going to keep this class to the half hour because I went overtime yesterday. So we're going to stop now here. And next day, we'll get into a little bit more. Let's see, where are we here next day? We'll be looking at, not that one, not that one. Yes, we'll be looking at magnetic fields and how magnetic fields work and how magnetic fields interact with each other. And yes, we will get into special relativity and general relativity more thoroughly when we get to the next unit, the last unit of the year.